So in these talks, I want to discuss various aspects of three-dimensional quantum field theory with so-called n=4 supersymmetry. And for the most part, it's not going to be topological. But the supersymmetry will still help us compute various things in these theories. And we'll see that, say, the path integral or operator correlation functions are still independent of some of the parameters, if not all of the parameters of the theory. Some things that I want to mention are relatively old on a physical timescale. In other words, known since the mid-90s. They were discovered by a group of folks, in particular Nati Seiberg and collaborators. Some of the things I'll discuss are much newer, in particular the study of boundary conditions. And compactification to 2 dimensions. Or rather, compactification to 2D has, of course, is a very natural thing to look at, and people have looked at it, but I'll try to say some of these things about it. One of the main motivation for discussing these theories here is that they seem intimately tied in to geometric representation theory. And I keep, sorry, it's probably not big enough. To geometric constructions of knot homologies. Which is also, well, this column on the big table. And symplectic duality. Which is kind of a new thing in math. So one of my goals is to simply describe how some of these mathematical ideas arise in 3D n=4 theories, following some ongoing work with Davide Gaiotto, Matthew Bullimore, and Justin Hilburn, and advised by many people, including Ben Webster and Kevin Costello, and a few others. Since the tools and intuition one uses in the mathematical discussion of these ideas and the physical discussion of 3D n=4 theories are really quite different. Building bridges like this between physics and math has great potential to produce new intuition and predictions and results on both sides. And in the present case, I'll touch on the first few new mathematical predictions that have arisen from the story. So tomorrow, just to list a few of them. So on Tuesday, in the course of discussion, I'll touch on symplectic n-ality, or what that should mean. And Wednesday, I'll give what I think is a new construction of projectives. Projective representations in categories O. I'll also talk about well, an AGT-like correspondence involving finite W algebras that has appeared in math in the work of Braverman and collaborators. I can't, at the moment, say anything new mathematically about that, but I can explain how it arises in physics. And on Thursday, I'll say a bit about category O and knot homologies, and a new a new approach to both category O and knot homologies via two-dimensional Landau-Ginzburg models. For O knot homologies, etc., which again can be the categories of boundary conditions in massive 2D LG models are called Fukaya-Seidel categories, and they've been very well studied. And the claim is that that theory applies to this case. OK. On the physics side of things, I should say tomorrow is going to be about moduli spaces in 3D n equals 4 theories. Wednesday is going to be about boundary conditions in 3D n equals 4 theories. And Thursday is going to be about two-dimensional reduction of 3D n equals 4 theories. And Thursday is also where the connection to the poster will happen and to theory X. Great. Aside from just talking about 3D n equals 4 theories, I would more broadly like to help familiarize you guys with the workings of supersymmetric quantum field theory and the types of questions one asks and the intuitions that arise from that. The goal is hardly to make you experts, but rather to help facilitate conversations that involve quantum field theory. So for the rest of today, I want to, well, it's going to be a disjoint lecture. So in the first half of the rest of today, I want to introduce you to some of the mathematics, or review to the best of my ability some of the mathematics that I'm going to make contact with throughout the rest of the talks. And then to get everyone on the same page, I want to review just the basic structure of classical and quantum field theory and some fundamental concepts that arise again and again. OK. Without further ado, geometric representation theory. In the version for simple Lie groups, which is the most familiar one, well, there's been a lot of work over the past 40 or so years on it, and some of the landmark papers are by Bernstein, Gelfand, and Gelfand in '76, Bailenson and Bernstein in the early '80s, and Bailenson, Ginzburg, and Sorgel in the mid-'90s. There's also been a vast generalization in recent years, proposed in particular by Braden, Licata, Proudfoot, and Webster, which is really the way I want to think about things, and I'll explain that. So let me begin with the SL2 example. So let me take my group G to be SL2, and recall that the enveloping algebra of SL2 is generated by three generators, EF and H, subject to the SL2 commutation relations. EF equals H. This H E is 2E, and HF is 2F. This algebra also has. Oh, wow. That was immediate. Yes. This algebra has a center that's generated by the Casimir element, EF plus FE plus a half H squared. And the full representation theory of U of SL2 is really horrible. BGG, Bernstein, Gelfand, and Gelfand, proposed to study a much simpler or a category of much nicer representation. So they defined an abelian category O of representations that were highest weight which means here that the action of the raising operator E is either locally nilpotent or locally finite, depending on the precise definition. And such that the representations decompose as a sum of their weight spaces, or really as a sum of their generalized weight spaces. Let me call it mu. So generalized eigenspaces with respect to the action of H, the carton. This category, this category decomposes into so-called blocks, where the blocks are generalized eigenspaces for the Casimir. So the statement is that O decomposes as a sum of O lambdas, where on each O lambda, the Casimir has eigenvalues a half lambda squared minus 1. And this is a convenient way to parameterize the Casimir. Obviously, this only depends on the on lambda squared rather than on lambda. So let me describe a little bit of the structure of category O. And I'm doing this in a great deal of detail because I'm going to come back to it over and over during the next few days. So for generic lambda, meaning not an integer, O lambda is extremely simple. It contains two irreducible Verma modules. Of highest weights lambda minus 1 and minus lambda minus 1. The minus 1 is a shift by the Weil vector of SL2. And they don't talk to each other. The hums between them are trivial, and hence the category is extremely simple. When lambda is an integer, however, and in general, what one wants to say is that lambda is in the weight lattice for the relevant group. So suppose, for concreteness, that lambda is greater than or equal to 1, then O lambda is a so-called regular block of the category, and it has interesting structure. So it's again generated by the Verma modules. But now there's a non-trivial hum. So the Verma of weight minus lambda minus 1 is a submodule of the Verma of weight lambda minus 1. In particular, there's a hum. And so one can create other representations. And I will describe them pictorially. So So let me draw a picture of the weight spaces. Where this is lambda minus 1, so this is minus lambda minus 1. The Verma of weight lambda minus 1 is infinite dimensional. And it has highest weight lambda minus 1. And I'll be drawing many pictures like this. The other guy starts at minus lambda minus 1, goes off to infinity. And so, of course, I can consider, so this one is irreducible, but the other one is not. So I can also generate category O using simple or irreducible modules. So these are Vermas, or so-called standard modules. And let's look at the irreducibles. It's called simple modules. So there's a finite dimensional irreducible of dimension lambda, in fact. So this is L lambda minus 1. It's a quotient of Verma lambda minus 1 by Verma minus lambda minus 1. And the other Verma is irreducible. So L minus lambda minus 1 is simply equal to the Verma minus lambda minus 1. OK, and finally, there are, well, finally for this talk, there are so-called projective modules. Projective in the sense that they're projective elements of this abelian category. But also, at the level of representation theory, the relevant defining property is that taking Homs out of them projects onto a weight space, and taking derived Homs out of them. So if P mu is a projective of weight mu, then it has the property that taking Hom into any other module M just projects onto the muth weight space. And they look like this. So one of them is simply the Verma module of weight lambda minus 1. This is Verma. The other one is an extension of one Verma module by the other in the only way that one can form such an extension. So let me write it in black so that it's actually visible. So P minus lambda minus 1 is an extension of Verma minus lambda minus 1 by Verma lambda minus 1. OK. And right, so what makes the structure of this projective module non-trivial is that H, the Cartan, is not diagonalized. It acts in Jordan blocks. It maps the small Verma into itself, but also across to the big Verma. So H has Jordan blocks that look like that. OK. And I've tried to phrase things in a fairly general way so that the extension to other Lie groups might make sense. But this is the general idea. One starts with, say, some Verma modules and takes successive extensions or quotients of them to build everything else. OK, now let me make a few observations about the properties of this category. So first, O lambda depends secretly on two parameters. It depends on lambda. Really, it depends on lambda squared, a value of the Casimir, the way I've set it up. But it's often more useful to think of lambda itself, lambda being the highest weight of being the highest weight of the representation with the highest weight in category O lambda. And two, it secretly depends on a choice of highest versus lowest weight. So I could have written the algebra using E and F, or I could have written it using F and E. And so there's secretly a second choice of highest versus lowest weight here. And if I had taken a lowest weight category, it would have looked almost identical. But a choice was made. I also want to note that the enveloping algebra, U of SL2, has a natural filtration. Where, for reasons that will seem perverse for the moment, I'm going to give E, F, and H all weight 2. Then, since the commutation relations reduce the numbers of E's, F's, and H's that I have, the commutation relations always decrease the grading of things in them. Right. Anyway, I get it. So I get a filtration. If I deform the commutation relations by some parameter h bar, so instead of saying that EF is h, I set it equal to h bar h, and so on for the others. I just stick an h bar on the right-hand side. And I think of h bar as a formal parameter rather than an actual number, so that I can give h bar some weight as well. Then the enveloping algebra is actually graded. This h bar version of the enveloping algebra is graded. Graded as U SL2 h bar or something like that. In other words, another way to say that is the commutators all have definite weight. And we'll see that coming up again and again. Now, Bailenson and Bernstein proved that this category, O lambda, was equivalent keep getting attracted to this poster. Was equivalent to a category of equivariant D modules on the flag variety. It's variant, twisted D modules on G mod B, which in this case is CP1. And in this equivalence, one interprets the weight, lambda, as a homology class, well, as a class in H2 of the flag variety with complex coefficients. and it tells you which twisting to take. Basically, lambda twisted d-modules. If you do, great. If not, I will give a much more hands-on construction of these things where it should become clear. So intuitively, D is some sheaf of differential operators, and there may be curvature when taking commutation relations of those differential operators. There may be curvature in that sheaf, and then that curvature is parameterized by lambda. In this particular situation, if lambda is an integer, so if, in fact, it's a class in H2 G mod B with integer coefficients, then we're looking at differential operators acting on sections of a line bundle over CP1. Where the first Chern class of the line bundle is lambda. And that's a very concrete way to say what I mean by curvature. Does that help? OK, now Braden, Licata, Proudfoot, and Webster put this idea in a much more general context. So
you say that the d-modules are equivariant as well as twisted. Which group are they equivariant for?
I'll explain in about 5 or 10 minutes. So they consider so-called conical symplectic resolutions. So a pair of algebraic varieties, M and M naught, where M naught is affine and M is a smooth resolution. Moreover, M naught is algebraic symplectic, or I often say holomorphic symplectic, and more generally hyperkähler. But the part that will be important here is that it has a holomorphic symplectic form. Capital Omega. Well, they both do, and the holomorphic symplectic form is preserved by the resolution. Hence, symplectic resolution. They require several other things. In particular, a U1 action on M that preserves, does not preserve, sorry, a U1 action on M, and that can be complexified to a C star action on M naught. I'll denote them as U1 epsilon and C star epsilon, where in both cases, the weight of the holomorphic symplectic form under the epsilon action is 2. And so they do something slightly more general and allow more general weights. But in 3D n equals 4 theory, this is always 2. OK. Now, in the BGG example, in the geometric representation theory, the relevant M to use is T star of the flag variety. And M naught is the nilpotent cone. of the given group. Note that a choice of resolution is related to a choice of class in H2 of M with real coefficients, which is if this is a hyperkähler resolution, then this is the Kähler class of the manifold M. In this picture, another U1 action is required. So I'll say in a second, the answer to the previous question about which action are things equivariant with respect to is this U1 epsilon.
Sorry, I'm just confused. So the map is always the Springer resolution, but you say that
It is, well,
you mean that you can give it with a different Kähler structure?
Yeah. So it always, I mean, no matter which way I resolve, it always looks the same. But there's some mileage to be gained by, well, so given one particular resolution, there's an ample cone in H2 where the Kähler class has finite volume, basically. There's some mileage to be gained by observing that, in fact, there are multiple ample cones that tile H2, and that I can kind of move from one to the other and get resolutions that essentially that look the same, but where, say, in the category of D modules, various objects are permuted, and so one gets a braiding action on the category by looking at different choices of resolution.
But you can think of the underlying space as always being T-star G.
Yes, I can.
Changing some parameters or changing some Kähler structure.
I can, yes.
But for other examples, like there will be honestly different resolutions of the same cone. Like for hypertoric variety or quiver varieties, you can use honestly different resolutions. Not even
Thanks.
isomorphic is.
In this case, you have like non-trivial flips and flops.
Yeah,
Yes.
exactly.
Yeah. Cool. Sorry? Yeah.
Sorry, do you explain the relative power of epsilon?
It's a label at the moment. I want to use consistent notation, and this is the beginning of it. It's to distinguish it from another action I'm about to discuss. Which, I'm sorry, the notation is not totally consistent with any of the literature. It overlaps with bits of it, but it is going to be consistent throughout the talk. So there's another U1 action. That's a hyperkähler isometry. In particular, it preserves the holomorphic symplectic form. And so one requires the space to have another U1 action that has fixed points, that has isolated fixed points.
Does that requirement have any physical meaning, or they should pose it because somehow they can't kill nothing otherwise?
Sorry, can you say that again?
Does that requirement do not have a physical meaning?
Yes.
Yes?
Yes. Yes. OK. And it can be extended to a C star action that is not a hyperkähler isometry, but that is a holomorphic symplectic isometry. And I was going to say how to do that, but I don't think I have time. So ask me later if it is interesting.
There's more than one way to do it.
There is a distinguished way to do it given a hyperkähler metric. given a hyperkähler structure.
Will you say what it is in this example?
I will draw a picture of what it is in the example. Give me a sec. Sorry for all of the delayed satisfaction.
Sorry, one more question. So what does the epsilon stand for?
It's a label. It is to distinguish it from C. Okay. So these guys define two objects. D lambda, which is a sheaf, that's a C star epsilon equivariant quantization of the holomorphic symplectic space M omega. And A lambda, that's the ring of global sections. In other words, a deformation, a non-commutative deformation of the ring of functions on M, which is the same as the ring of functions on M naught. And the theorem is that, at least in nice cases, the categories of D modules and A modules are equivalent. And, well, I need to add some qualifiers in each case. And the qualifiers involve the extra symmetry. So in this, on the left-hand side, it's D modules with support on, oh, you guys probably can't see that. So let me write it up here. So it's D modules with support on a holomorphic Lagrangian subspace of M. Defined as the points that have limits under the U1 Xi action, under the C star Xi action. So it's points in M with limits under C star Xi as the parameter goes to infinity. And over here, the A modules are required to have a locally finite action of A+. So U1 Xi gives a grading on the algebra A. And there's some subalgebra A+ that has all positive weights. And we're requiring that the action of this is locally finite. So that's the equivalent of the highest weight condition that existed for SL2. And here's the picture. So for SL2, M is T star flag. So it's T star of CP1. And we want to draw a slice of it that's invariant under this Xi action. So what does this Xi action do?
So is the circle is P1 and
Oh yeah, I'll explain. So I've drawn the base, that's the sphere. U1c rotates the base and gives it a distinguished north and south pole. And then I've drawn the fiber at the north pole and the fiber at the south pole. And U1c also rotates the fibers. The locus M plus consists of the base and the fiber at the south pole. And so how do I get that? The complexified C star action, the non-compact part of the C star action pushes everything up. And a really nice way to think of it is, well, isn't the hyperkähler situation, where the non-compact part of the C star action comes from gradient flow with respect to the real moment map for the U1. Since U1 is a hyperkähler isometry, it comes with a triple of moment maps, a complex moment map and a real moment map. The real moment map increases in the direction I've indicated. And the complexification of the U1 comes by looking at gradient flow with respect to that real moment map. So M plus is another color. Is the base and the south pole fiber. And then what happens? The modules that I drew on the board before map to D modules supported on the base or the south pole fiber or some combination of the two. So for example, the simple of finite dimension is supported exclusively on the base, whereas the Verma modules, so the simple L lambda minus 1 is supported on the base, whereas, say, the Verma module L lambda minus 1 is the lambda minus 1 is supported on the base and the south pole fiber. And so in this very simple case, the picture with weight spaces becomes the picture on this so-called core of the manifold M. OK. Good.
This is just a small basic question, which is, why do you write that the functions on M are the same as the functions on M0?
Right. So that's a property of these resolutions. So in particular, the holomorphic functions can't see the real resolution, and I don't think it's necessary here. But let me just say again that M naught is affine. So in fact, one way to define M naught in this case is to say that it's spec of C of M. I should have also said much earlier what the special thing about the epsilon action is, the one that everything's done equivariantly with respect to. This C star epsilon shrinks the fibers of the cone. So M naught is some cone, and C star epsilon shrinks everything to the conical plane. That is crucial, and saying it now. Right. I should probably apologize as well in advance for any imprecise mathematical statements I make. Hopefully, most of them are going to come today, but feel free to correct me. OK, so right. Bailenson, Ginsburg, and Sorgel showed that there's an isomorphism between category O for G and, I believe, category O for its Langlands dual. There's an equivalence in a very non-trivial way. In the example I gave you, T star of CP1 is related to T star of CP1. But the equivalence shuffles things around. And the extended observation, and in some cases theorem of BLPW, is that in general, there are pairs of so-called conical symplectic resolutions. I keep forgetting what the exclamation point is called. You guys like to use this. Shriek, right. Such that OM is equivalent to OM shriek. More precisely, in nice cases, both of these categories are Koszul, and this is a Koszul duality. That exchanges simples on one side with projectives on the other, which is why I mentioned them half an hour ago. And it exchanges the roles played by the parameters or the groups or the labels that I have informally referred to as lambda and xi. So in each case, there's always some Casimir or highest weight parameter, and there's also, there's a Casimir parameter, and there's a highest weight parameter, and the roles are reversed. The simplest non-trivial case after T star of CP1 is T star of CPN, which I don't think is in the original BGG type setting. So T star of CPN.
This isn't an example of like a
Yeah, no, it's certainly not T star of G mod B, but it is T star of a partial flag variety. This is dual to a Zn plus 1 singularity, to the Krepin resolution of a Zn plus 1 singularity.
Did you explain what is constructing this resolution, or what is constructing this duality, or are you just stating this duality?
I am at the moment stating an observation that there exist lots of pairs of spaces for which the categories are dual in a very special way. I think it is a conjecture, at least it certainly should be a conjecture. It certainly is physically that given a space M that has all of the properties I've discussed, there exists some M shriek whose category O is dual to it. It is far from obvious in general how to construct M shriek. And the physics is that these end up being branches, two different branches of the moduli space of a 3D n equals 4 theory.
Sorry, I didn't understand the roles of lambda and xi. You described them as interchanging the Casimir and the highest weight, but I thought lambda was both.
Sorry, I meant a highest. Yeah. So xi plays a role of determining. It splits it splits the algebra into raising and lowering operators. So it determines highest versus lowest weight, whereas lambda determines a Casimir. Yeah, it's the same C. So the C star C action was doing that geometrically. And gave us a direction that D modulus had to go in at infinity. Which is the same as saying I want highest weight representations where the highest weight direction goes up as opposed to down.
Tudor, maybe
Yes.
you could say where C and lambda live. So, like, I mean, because part of the conjecture is right that these parameter spaces are the same.
It looked like the first one was always a Z, and the second one seemed like
I can. Yes. I think I can. I would actually much rather do it tomorrow. So they have to do with, well, so lambda is clear. So lambda lives in H2 of M with some kind of coefficients. We make them C for the moment. C lives in the cartan of a flavor symmetry group, of a global isometry group on the manifold M. So M has some maximal isometry group, G sub M. C lives in the cartan of GM, possibly complexified.
Just for like concreteness, it's like the Hamiltonian isomorphisms that commute with epsilon.
Yeah. Sorry. I mean, it's thanks. Yeah. Let me call them hyperkähler isomorphisms to be precise. Okay. And that makes it even more surprising that this duality exists that exchanges these parameters that look very, very different. Thanks. Okay. So that's all I wanted to say about math. Let me say some things about physics in 5 minutes. Works. So I'll get back to, I'm going to get back to lambda and C tomorrow. So what do I want to say? Let me just start with classical field theory. So a classical field theory is about solutions to partial differential equations on Rd or maybe some other manifold Md. PDEs like the Laplacian of phi equals m squared phi, where phi is some function on R to the d. In general, phi can be a section of various bundles on R to the d, and the equations have to make sense on those bundles. Phi and the functions, the sections involved in these equations are the things called fields. This is incredibly basic, but seemed worthwhile to mention. Now, there might be several fields. That can be coupled So it means that that the PDEs are coupled equations in terms of these multiple fields. Sorry?
When you say PDE, do you mean vector bundle with connection?
No, I mean partial differential equation.
Okay.
I mean, sometimes, I mean, this is certainly not, as far as I know, having to do with a vector bundle with connection. But
So do I understand correctly, coupled doesn't mean anything, like not coupled would mean something?
well, so
I mean, you can imagine being able to separate your PDE into two,
yeah.
you know, when you have a list of equations, you can imagine being able to separate them into two pieces where none of the fields in this one interact with the fields in that one. That would
I mean that it's exactly that. So you can, either you can solve the equations separately for each of these sections or each of these functions, or you can't.
Is it like
And coupled means that you can't. In other words, so I mean they will literally show up as terms in the PDs that involve both types of fields. It's
right. Yeah.
yeah. Right, and you can decouple them perhaps by a coordinate transformation, but yeah. Okay, I should have done more of this. So the basic question one wants to analyze is a scattering problem, the basic process. Namely, when given some initial configuration of fields, well, so first we split RD into a time and space directions. Given some initial configuration of fields, in the space directions, say some waveforms moving in a certain direction, at time 0, one wants to know what happens at very large time in the future. This is the so-called scattering problem, and one simply solves the PDEs to figure out what the solution late in the future is going to be. And one can require the theory to have several symmetries and several special properties. For example, one can require that the equations of motion, those are the PDEs, so these are also called equations of motion. One can require that the equations are invariant under Lorentz transformations. So if RD is actually Minkowski space with a Lorentzian metric, there is a Lorentz group that preserves the metric. It can be extended to a Poincaré group that includes translations as well. And one can require that the equations are invariant under that, and this equation in particular is. There are also global and so-called global and local symmetries. Global, or often called flavor, symmetries is some symmetry that doesn't depend on position in R to the D that leaves the equations of motion invariant. So if, for example, phi is a complex valued function, then I can rephase phi, where alpha is just some constant, and those equations are going to be invariant. And then there are gauge symmetries that are basically the same thing, except the transformation parameter does depend on position in R to the D. And so those are sometimes called local as opposed to global symmetries. And that this equation is not invariant under a gauge symmetry, but if I made phi into a section of a bundle with connection, and I transformed both the connection and phi at the same time, then I would get an invariant equation. So with appropriate covariant derivatives, I get an equation that has a gauge symmetry. Most relevantly, perhaps most familiarly, one can require the theory to be Lagrangian, which means that the equations of motion come about as critical points of some Lagrangian density. So one requires that the equations of motion come about by studying a variational problem, looking at variations of some Lagrangian L integrated over r to the d, or md. The critical points are given by Euler-Lagrange equations, and one wants those to be equations of motion. So in this particular case, L equals d mu phi squared minus m squared phi squared is the Lagrangian density, and Euler-Lagrange equations just set d mu dl d mu phi equal to dl d phi. And that takes the form of the equation I wrote on the board. OK. So all of these properties have analogs in a quantum theory where a path integral is involved. I'll maybe say a bit more about that tomorrow. If I can have, I think, another 3 minutes. And there's one important point that I wanted to make in a quantum theory, but that really holds in a classical theory as well. And that's dependence on energy scale. So, if I look at the theory at different distances or different energy scales, the equations of motion and the degrees of freedom in the equations of motion might be different. And that's something. That's a very important feature of quantum theories and is even more involved there, but you can see it in the classical world. So in this case, I have this parameter m in the equation. If I send m to infinity, actually let me do the opposite limit. If I send m to 0, then the equation of motion just sets the Laplacian of phi equal to 0. It's a standard wave equation. And if one knows a bit about solutions to a standard wave equation, one knows that wave packets just propagate infinitely without any attenuation. So phi is so-called free field. Propagation to infinite distance. On the other hand, if m goes to infinity, then the only possible way to solve that equation is to set phi equal to 0 everywhere. And this is a so-called infinitely massive theory. And we would say that phi just sits in a vacuum. The vacuum is, well, in this case, it's what you get by setting all the derivatives to 0 and looking at solutions to the equation. In general, it's a 0 of the potential energy functional that enters the Lagrangian, which here is this. So there's some potential energy density that's local in phi. It's m squared phi squared. And a minimum of the potential energy is just at phi equals 0. That's the vacuum. And that's the only solution you get in the infinite m limit. There are no propagating degrees of freedom. And a better way to say this, so I've introduced this M. M is a mass. So anytime a parameter anytime there's a parameter multiplying a quadratic function in the fields, it's generically called a mass parameter. The reason for that is it comes from dimensional analysis. So in a world where the speed of light and Planck's constant are set to 1, energy has the same dimensions as mass, and as well as inverse distance and inverse time. And in the problem at hand, I don't really care what dimensions phi has, but at least not for the moment. But the equation involves two derivatives. And so that's, in terms of mass, that's mass dimension 2. So dimension of that is 2 phi. So the dimension of this is also 2. And indeed, it functions like a mass. So a better way to describe this vanishing of degrees of freedom is to say that at very high energy, is to introduce an energy scale. Capital lambda. This also has, since energy and mass have the same dimension, I can consider a dimensionless quantity, m over lambda, which is actually a number. And it makes sense to talk about its value. At very high energy, so this is some kind of dimensionless effective mass. So at high energy, m over lambda is very, very small. The theory is effectively free. It's like I was setting m to 0. At low energy, m over lambda is huge, and the theory is effectively massive and stuck in a vacuum. So often in physics, we talk about high energy and low energy behavior of a theory. And it can be translated into a statement about how the parameters in the theory are related to the energy scale that I'm measuring the theory at. High energy is usually called the ultraviolet regime of the theory, and low energy is called the infrared. I could stick wavelength into this comparison of dimensions. And high energy means super short wavelength. Low energy means super long wavelength. The words come from particular field theories that were analyzed long ago, but I just want to point out that what UV and IR are supposed to mean. OK, thank you.